Good morning, I'm Manuel Zarzo. We are in Unit 8 Regression, and in this video I'm going to talk about interpretation of regression models. Here, this is a scatter plot of the y versus x, and we can see like a cloud of points with a positive slope. So if we fit a straight line, this line has a positive slope, and that corresponds to a positive correlation coefficient. We can say that the degree of relationship is weak. We will say that there is a weak correlation because the variability of the points with respect to the line is quite high. Okay, so we can make a prediction, but that prediction will present like a high error. Okay, this is a totally different case. The points are perfectly aligned, so this is the maximum positive correlation possible, and that corresponds to a value of the correlation coefficient equal to 1. Remember that this correlation coefficient ranges from -1 to 1. Negative values correspond to a negative slope, and positive values correspond to a positive slope. This is a case where the fitted line has a negative slope, and then the correlation coefficient will be negative. And then we can say that the correlation is like moderate, because the points fit better to the line compared with this first example. In this case, this is again, the points are perfectly aligned, but the slope is negative, so the value of the correlation coefficient will be -1. And in this example, we cannot see any kind of trend. So we will say that the degree of correlation is 0, so the variables are not correlated, and then the correlation coefficient is 0. This correlation measures the degree of correlation. If there is no correlation, obviously this coefficient becomes 0. And then if we fit a regression line, the line becomes with a horizontal line with a null slope. And this is a special case because we can fit a predictive model. Okay, we can see like a curve, so that we can fit a curve like this to make predictions. But if we just fit the equation of the straight line, that line will be horizontal, and for that reason the correlation coefficient will be 0. And then it is a good opportunity to explain that this coefficient is called linear correlation coefficient. So from a linear standpoint, there is no correlation between the y and the x, but if we fit a quadratic model, it fits pretty well to the model. It fits pretty well to the points. Then there's a need to define another goodness of fit coefficient, which is called R-squared coefficient of determination. In this case, if we compute this coefficient of determination, it will present a positive value because we can fit a curve to make predictions. Okay, this is another example. If we fit a straight line, the line will be positive, so the correlation is positive. But in this case, we can see that if we fit a curve like this curve fits better. So in this case, we will say that there is a positive linear effect because the slope of the line is positive, but there's also a negative quadratic effect. This kind of curve corresponds to a negative quadratic effect. If the curve would be something like that, upwards, that would be a positive quadratic effect. In this case, if we fit a straight line, the line will be horizontal, so the correlation coefficient would be 0, okay, not correlated. In this case, it's a special case also, because we can think that we can fit a vertical line that fits pretty well, but actually this interpretation is wrong. Actually, there's no correlation. The correlation coefficient is 0. Why? Because if we just take the range of values, the range of variability on the x, and we just magnify that, this situation will become this situation. Okay, so actually we can see that when the x increases, there is no trend to increase nor decrease. Okay, and this is another case, another example of variables with no correlation. The slope is horizontal. And then this is a case of a negative linear effect, a negative correlation. But imagine that here we have points that go down, that decrease. And then imagine that in these central points In this central part, the points basically follow like a horizontal shape. And then again, here in this last part on the right side, imagine that again the points go down. Well, that would correspond to a cubic effect. Okay, so if we have like a trend where it goes down, then goes horizontal, and then goes down again, we can fit a polynomial mathematical equation with a cubic term to fit the data, and then we can study if that cubic term is statistically significant or not. Well, and then finally, this is an example of a quadratic effect, similar to the one that I explained in the previous slide. Good. So examples of correlation coefficients. Here, this is like a chart explaining like most of the possibilities. The first case is a maximum correlation, maximum positive correlation. The points are perfectly aligned. Then here we have an example where the correlation is more or less strong. For example, 0.1 would look something like this. Then here, these are examples of moderate weak correlation, approximately. Well, in statistics, there is not like intervals of the correlation coefficient where we classify that as weak, moderate, or strong, because it depends on the area of the sciences. There are sciences where strong correlation implies that points are nearly aligned, and we can find that in other sciences values of are 0.85 or something like that might be considered as a strong correlation. These are examples where the correlation is null. We cannot see any kind of trend increasing nor decreasing. And then the last examples are the same but with a negative correlation. That would be like moderate weak, that would be strong, and finally that would be the maximum possible correlation because the points are aligned but negative. Okay. Now, interpretation of the relationships between the two variables. The example that I'm going to consider is the following. Imagine that the government wants to promote the use of computers among citizens. Then imagine that we have a study that reveals that in Spanish homes, the annual spending on computers is positively correlated with the spending on shoes. Okay, imagine that that is true. Okay, then can we think about this conclusion? The government decides to promote this spending on shoes by lowering the price in order to stimulate or to incentivize the use of computers. Does it make sense? Well, if you think for a while, I think that it's quite obvious that it does not make any sense. And then we'll have to think about this interpretation. Well, so if when the number of children in a family increase, and also if those members of the family have a higher age or family members with a higher level of studies or higher family income, then that produces a higher spending on shoes, and also produces also is positively correlated with a higher spending on computers. Okay, so that explains the observed positive correlation between both variables. But there is not a cause-effect relationship. It means that if I increase the spending of computers, it will not produce a spending on the shoes nor vice versa. Okay, so this is called a partial dependence. So we have observed two variables with a positive correlation, but it's not a cause effect. It's called partial dependence. There are other variables that explain that. Example. Now let's think about this. Imagine in a chemical process we observe that certain quality parameter that we call Y is positively correlated with temperature at a certain point. Well, conclusion. If we want to increase the quality of our product, then the recommendation could be to increase the temperature. Does it make sense? Well, I think that for many people, for many engineers, thinking about that, they will say, yes, if I find a positive correlation between them, that makes sense. But the answer is no, that is not correct. And the reason is exactly the same as in the previous slide. So the rule is that the observed correlation between two variables does not imply necessarily a cause-effect relationship. okay? And this is important. So basically the idea is the same as in the previous slide. So when we have correlation, positive or negative correlation between two variables, that interpretation can be based on different reasons. It can be one-way cause-effect dependence. Okay, for example, imagine that I find a correlation between the room temperature and the power consumption for heating. For example, if it is very cold, I will need power consumption for heating the room, and if it is hot, that is not required. Yes, so there's a correlation between X and Y, so we can say that this is a cause-effect relationship. Or the amount of rain and the amount of water in the reservoirs. Obviously, if it rains a lot in the region, so the amount of water in the reservoirs in that region will go up. Cause-effect dependence. Or the speed of a computer processor and the time to carry out certain computational operation is the same. Cause-effect dependence. But also we can have partial dependence of one or more variables. For example, genetic characteristics can affect the height of a person and also can influence the weight of a person. So we can find a positive correlation between height and weight of a person, but it's not a cause-effect relationship. It means that if a person increases the weight, we will not expect also an increase of the height. Also, the family income, for example, will influence the expenses in shoes of the family. Well, this is an example that I explained in a previous slide. Or the attendance of theory classes. Is it related to the final score in the exam? Well, maybe yes. So it's something that you should think. Or number of hours to study statistics. Maybe is that correlated with the final score in the exam? I think that probably yes. But is that a cause-effect relationship or maybe just a partial dependence? Okay, probably there are other factors. And then we can have interdependence between two variables. Okay, it means that it's not clear what is the X and what is the Y. So we can see two variables are correlated, which can be positive or negative, but it is not clear if x1 is a function of x2 or if x2 is a function of x1. It is called interdependence. For example, imagine that there's a positive correlation between the score that a student gets in mathematics versus the score that the students get in statistics. But is this first score a function of the second, or is the second a function of the first one? Well, it does not make sense. I mean, it's both situations would make sense at the same time. So it's called interdependence. Or the weight of a person versus the height. We can check that there exists a positive correlation between both variables. But is the weight a function of the height, or is the height a function of the weight? Well, it's like unclear. It's an example of interdependence. Or in a married couple, we can find a positive correlation. Actually, it exists between the age of a husband and the age of a wife. But which one is the X and which one is the Y? Well, it does not make sense in this example. It's another case of interdependence. And here I finished this video about interpretation of regression models.